So before we go on to looking at nanostructures, let's see how magnetic materials behave in the bulk. So if you have a magnetic material which is a bulk material, and you start magnetizing it from a demagnetized state, that is here. So in the demagnetized state, the magnetization is 0, and the diagram here shows you why the magnetization is 0. The bulk material consists of different crystallites, and each crystallite has its own easy axis. So for example, this crystallite will have an easy axis along the right direction. This one might have an easy axis along this direction, so that when the material is in a demagnetized state, the magnetization along each of these red boundaries, which is known as a domain, points along the easy axis in that particular region. So as you start increasing the magnetic field, what happens is that the domains that are with the magnetization in the direction of the applied field, these start growing at the expense of other ones which start shrinking. So magnetization takes place by domain wall motion. The red lines here indicate the domain walls. Until the whole material is magnetized in one direction, it becomes a single domain material, and there you produce the saturation magnetization. Any further increase in field will not change the value of the magnetization. When the field is reversed, then there is a finite remnant magnetization left over. The reason being, first of all, the exchange interactions which I mentioned, and second is that these domain walls are not, their motion is not completely reversible in real materials, because real materials have defects and the domain walls get pinned or stuck in those defects, and as a result of which the domain wall motion becomes irreversible, and this irreversibility is reflected in the remnant magnetization. And to reduce or to deepen the domain walls and reduce the magnetization to 0, one needs to apply a negative field in the reverse direction to the original magnetizing direction, and this is known as the coercive field. So this is generally the behavior of a ferro or ferrimagnetic bulk material, where magnetization takes place by domain wall motion or domain rotation. Now what happens if I keep shrinking the size of my material? Let's just go back for a little while. So these domains in materials, they can be of the order of microns or even 100 microns or something like that. But what happens when I shrink the size of my sample below a micron or below the size of a single domain? Then in that case, I end up with single domain structures or single domain particles. Now the particle is so small that it cannot support a domain wall, and a domain wall has a finite width. So if I make the size of the particle smaller than the width of the domain wall, then it will not be able to support a domain wall, and the particle will exist in a single domain state. So this happens below a critical radius, RSD. SD stands for single domain. Magnetic particles exist in a single domain state. So because they exist in a single domain state, of course, magnetization or demagnetization cannot occur by domain wall motion, because there are simply no domain walls. The particle is just too small to support a domain wall. So what happens in this case, how are single domain particles magnetized? There are two different cases. One in which the applied field is parallel to the easy axis. So for example, the blue here is a single domain particle. The red line with the arrows indicates the easy axis of this particle. So it's equally easy for the magnetization to align itself either upwards or downwards. Energetically, both alignments are equivalent. So what happens if I apply a magnetic field along the easy axis of this particle? Now what the anisotropy energy does is that it holds the magnetization fixed along the easy axis because it's energetically favorable. It will not allow the magnetization to move away from the easy axis until I apply a field that is large enough to break this coupling. Because as I told you, there is a coupling energy which couples the applied field to the magnetization. That was EH, which was the first term in our energy equation. And there is a coupling energy which pins the magnetization to certain crystallographic directions, which is the anisotropy energy. So it's basically a competition between these two energies. So if I apply a field that is large enough so that EH becomes larger than the anisotropy energy, then the magnetization will flip its direction and align itself anti-parallel to the easy axis. That is, it will become negative. So suppose I have a particle magnetized along the positive field direction. There is a saturation magnetization. I make the field negative, but the magnetization does not change its direction. It remains fixed. This is because the anisotropy energy is preventing the magnetization from changing its direction until I come to a field which is large enough to break the or to overcome the anisotropy energy, and the magnetization then switches abruptly to the negative field direction. So in this case you have magnetization reversal by abrupt switching, and there is a large coercivity and remnants. And you can see that this has applications, particularly when you want to make hard magnets. You want single domain particles because you can obtain large coercivities and large remnances. The other case is where you apply a field perpendicular to the easy axis. Now what the field does is that it will apply a torque on the magnetization, and this torque will rotate the magnetization towards the field direction, that is along the right hand side. So here magnetization reversal occurs by rotation. So here you have the field saturated along the easy axis, and as you start increasing the magnetic field, the magnetization starts turning away from the easy axis and becomes perpendicular to the easy axis, and so in this case you have zero coercivity and remnants. And a very important feature when you need to look at magnetic nanoparticles is the phenomenon of superparamagnetism. This is extremely important. It can be used for advantageous purposes, but in some cases or in some application it becomes a nuisance. So we need to understand superparamagnetism and how to deal with it or make use of it. This is also something that occurs in single domain particles. So if the blue one here is your single domain particle, the red arrow is again your easy axis, and the magnetization vector is depicted in yellow, then there is an anisotropy energy barrier. We are assuming uniaxial anisotropy here. So the anisotropy energy barrier is K times V. If you recall, we had the anisotropy energy was kV sine squared alpha. So the barrier that the magnetization has to overcome in going from the positive direction to the negative direction will be over the value of alpha equal to 90 degrees. So that sine squared alpha becomes 1, and the height of this barrier is then K times V. The available thermal energy which the magnetic particle has at its disposal is greater than this barrier, then the magnetization can overcome the barrier and change its direction. So if the available thermal energy is smaller than the anisotropy energy barrier, okay, then the magnetization is pinned either along the easy axis or in the opposite direction. The energy, the thermal energy, which is indicated by this dashed line here, is simply not enough to allow the magnetization to overcome this energy barrier and flip its direction. But what happens when we go to the nanoscale? What we're doing is we're reducing the volume. When we are reducing the volume of the particle, when we are going to the nanoscale, you're basically reducing the anisotropy energy barrier. So this barrier height comes down. And now if it is smaller than the available thermal energy, then the particle can spontaneously switch its magnetization, and as a result of that, on the average, you will measure zero magnetization and zero field, because this process is associated with a relaxation time of 10 to the power minus 9 to 10 to the power minus 11 seconds. And on the average time scale, or on the time scale of most measuring instruments, this flipping time is way too small to be measured, for the change in direction of magnetization to be measured. So you just measure an average, which is zero magnetization. This means that small particles become thermally unstable above a typical temperature Tb, and Tb is known as the blocking temperature, and this is roughly the temperature where the thermal energy becomes of the same order of magnitude as the anisotropy energy, so that the anisotropy energy barrier can be surmounted. So if the temperature is larger than the blocking temperature, then the particle will behave superparamagnetically. That is, its behavior will have its magnetization hysteresis behavior, or let's say its magnetization curve will show zero coercivity and zero remnants, zero magnetization at zero field, because the magnetization is just flipping at too fast a rate for us to be able to detect it. However, if we are below the blocking temperature, so for the same material, it's just a size effect. So if you are below the blocking temperature, then you have ferromagnetic behavior and you find a magnetization hysteresis loop. So in this case, we are shifting. So the first case, the superparamagnetic behavior, corresponds to a thermal energy which is somewhere up here, close to the peak of the anisotropy energy barrier, and the second case corresponds to thermal energy which is somewhere down here, so that the magnetization is locked in either in a direction either parallel or anti-parallel to the easy axis. So what happens when we go from bulk to the nanoscale? A very important parameter when we're studying magnetization is the coercivity. And what happens is that as you go from very, very small particles, the coercivity is zero, which, as we saw, was the case for superparamagnetic particles. These have zero coercivity. As you go to a certain critical size, which is the limiting size for superparamagnetism at a given temperature, then the coercivity increases. So here you have a stable magnetization, and this region is that of single domain particles. After you have crossed a certain limit where you are beyond the minimum radius for single domain behavior, then you have multi-domain behavior. That is, your sample breaks up into domains, and here the coercivity decreases with increasing particle size. Okay, so typically in most materials, the superparamagnetic radius is less than or equal to 5 nanometers at 300 Kelvin, and the single domain radius is less than about 250 nanometers at 300 Kelvin, but this varies from material to material. So these are just rough order of magnitude numbers to give you an idea of the range of these critical radii. So you can see that single domain particles, this is where we end the nanometer range. And here we have two very distinct behaviors, one where the coercivity is zero and one where the coercivity increases sharply with particle size, and in both these regions we have different applications for nanomaterials. And this behavior of the coercivity offers us several issues and opportunities. For example, for recording applications where you want data to be stored magnetically, you would not want something that is superparamagnetic, because you will not be able to write any information on your magnetic hard disk. It would just go lost. That is why, if you remember, in the old days where there were floppy disks, you were required or instructed not to expose them to high temperatures. That was the reason that the magnetic data would be lost, because the individual bits of data there might become superparamagnetic. So, but for biomedical applications, superparamagnetism is actually something that is sought after, because superparamagnetic materials, as we have seen, have zero remnants and zero coercivity. So when you remove the magnetic field for a biomedical application, they become non-magnetic, and it is easy to remove them from the biological system. On the other hand, ferromagnetic particles which have a remnants would attract each other due to their magnetic remnants, and they would form agglomerates, which is not desirable.